Okay, perfect. So Bhavani is an assistant professor with the University of Luxembourg. He's been working on several topics related to MIMO wireless communications and radar. And he's currently coordinating the radar-related activities within his group, SIGCOM. And yeah, so we look forward to your presentation.
Yeah, thank you, Hamdi. Thank you, Marie and Giuseppe, for providing me an opportunity with this talk. I'm sort of trying to look at a bit more exploratory topic on using large-scale aperture arrays for integrated sensing and communications. Massive MIMO has been sort of reaching its maturity for communication, but things are yet to begin for radar, and so naturally for integrated sensing and communications. So I should start the presentation with acknowledgements to my colleagues listed here for their support, and also the funding agencies, the ERC grant agnostic and the Luxembourg National Fund, which funded most of these activities. So I would quickly present the joint radar communication. You've been looking at it in these talks, but sort of try to give it from a more radar perspective, different topologies very quickly. Then what does MIMO mean in radar? And then we sort of move to the massive MIMO for GRC or integrated sensing and communications. So radar performance, as with the communication, the performance of radar improves with bandwidth. It gives us what we know as the range resolution, the ability to discern two closely spaced objects. Here is a quick example. We have two cars, and then at a lower bandwidth, you would see a big blob, which you cannot distinguish between the two cars. You could look at the x-axis as range and y-axis as the speed. But if I have a higher bandwidth, then you're able to discern the two closely spaced cars. So this is why in applications like autonomous driving, where you have to clearly distinguish between a signpost and something else, you would need very high resolution and bandwidth. So this requires look into the radar spectrum allocation. Typically, the radar bands have always been used. There have always been coexisting communication bands, and more so recently with the crowding of mobile and Wi-Fi networks. The problem with radars is that they need to use the full bandwidth because they need resolution, and they need to do continuous transmissions because in surveillance you would need to do that. And so with this crowding, so there is always a need for radars and communications to share the spectrum. This is not something that is happening very recently, but it has been evolving for some time. In 2015, there was already an interest in DARPA for enhancing spectrum, enhancing access to the radio spectrum, where people are looking at radar and communication together. And then there has been some, further on this topic, there has been some shifts from radar to communication as well. And this is also another motivation for radar to work with communication. In C-band, previously in a particular band, it was allocated to the Department of Defense for certain applications, but that allocation was very, very poor because it was surrounded by communication applications, and then it was of limited use, and then it is now moved to wireless communications. Similarly, in the K-band, 24 gigahertz sensing was used for vital sign monitoring, for example, breathing and heart rate using radars without the need for any medical instruments, and then also localization. But now it has also been used, allocated to 5G in many US cities. So in that sense, there is a need for coexistence of radar and communication. And to understand what this entails means you have to understand what different topologies exist. So there are basically two topologies. One is coexistence, where the two systems continue to operate, but they adapt the transmissions to avoid interference to one another. Or the co-design problem, where there's essentially one system that does both the radar and the communication for functionality. They share antennas, they say share waveforms, so on and so forth. So any attempt to find any massive MIMO solution should be tailor-made to the different topologies that we look for. Okay, and this has been mentioned already that in 6G, this joint radar communication has been looking. This is sort of an interesting topic, and there's already an ETI in ComSoc for this. Okay, so very quickly, if you look at this MIMO, massive MIMO for radar, and then sort of look at the very obvious thing. The first thing that we're going to look at is the radar performance in a spatial domain. So we looked at the spectral domain with high bandwidth. So what happens in spatial domain? And this is a very classical use case. We would have a truck and then a kid that is cutting across the street in front of the truck. The problem here is that the truck reflects largely because there's a very strong reflection. It's a metallic surface, and the kid has a very low reflecting surface. So you have a very weak target in the presence of a very strong target, and then you have to identify them. If you have enough bandwidth, maybe you could look at it from a range problem, but then the problem here is that the truck has a much stronger reflection, so it's a weak, strong target. And if they're probably in the same range, you should have to look at it more from an angular separation. So you would need very good angular resolution in these cases. So the question now is, in the radar community, is angular resolution a final frontier for radar? Here is a quick picture that I took from the internet. Here is a picture of how a scene would be imaged by a LiDAR. And this is the highest resolution radar possible. And you would see that there is still some things to be met, the radar to sort of develop on. The resolution is still not so high. So the angular resolution in radar depends on the number of antenna elements, typically. And then we also have the concept of super resolution, where you have signal processing mechanisms that break this relation. So you have these algorithms like music, Esprit, which break this relation, but then they have another constraint that the number of sources that you could resolve depends on the number of elements. So that you could resolve two sources which are very close to each other, but the number of such sources you could resolve is again limited by the number of elements and the number of apertures, the larger aperture. So the focus now is to look at the aperture, which gives us the number of antennas. The first thing that we sort of look at is the obvious one, where you have a large phase array where you want to form a beam. And if I have a single, this is from ML's slide set, so just to illustrate. So if I have a single antenna, it's unidirectional. And if you have a couple of antennas, we could form a beam. And if you have a much larger number of antennas, you could form a much highly directive beam, in a sense that all the electromagnetic energy is focused in a particular direction. Not only that, you would also have the side lobes, which are minimal when I have a better directivity. So if I have a lot of antennas for the radar, it is very good in terms of for a single target, you're putting a lot of energy in one direction so that the reflections are also strong enough. So you could detect a weak target better. And then you're also not putting any energy in other directions so that it's not picking up any interference or clutter. And then if you have multiple directions, now you're sort of having pencil beams, so you could sort of have a better angular resolution. The only problem with large antennas with beam forming is the implementation issues. For example, there could be a lot of mutual coupling between the antennas. And then you would, of course, require a lot of hardware and so on and so forth. And in many applications like automotive, you don't even have enough real estate to put all these antennas. So this leads to the concept of MIMO radar. In the MIMO radar, you would have two arrays, a transmit array and the receive array. So for example, the blue is the transmit array, the orange are the receive arrays. So there is a particular spacing of the configuration of the antenna arrays and the transmit arrays and the receive arrays. So the way and the transmit arrays transmit mutually orthogonal waveforms. So if you have 10 antennas, we're transmitting 10 different waveforms, and these are mutually orthogonal. The orthogonality is again defined based on the context, typically the inner product or the autocorrelation, the cross correlation. And then the idea is that when I have this formulation, you could actually have a much larger array using T transmit, R receive. You could have T times R elements. So it gives me a much longer virtual array with very few elements. So this is the idea that you could still have virtually a massive antenna system, but with few physical elements. And then you could classify it as collocated MIMO or widely distributed MIMO, depending on whether it's everything is collocated or all the antennas look at particular target having the same reflectivity, or it looks at the target from different perspectives. Okay, quickly comparing with the phased array, you see that everybody transmits all the antennas transmit the same waveform, and then it forms a coherent beam. That is not the case in MIMO radar. Everybody transmits it's a mutual orthogonal waveforms, and the MIMO radar transmits is a sort of isotropic radiation, while the phased array has a directive radiation. So if you want to track something, you would probably want a pencil beam. So phased array is better. While if I want to search a wider volume, MIMO radar is better. And so you have comparative advantages and disadvantages between the phased array and a MIMO radar with a particular configuration here. Going into a bit of math here, the reason I'm trying to come is to finally link it to the waveforms and sort of bring into massive MIMO class problems in communication. So when I have a MIMO radar with multiple antennas, so the number of sources that can be resolved is given by this classical formula. It ranges in this you have, depending on the number of transmit and number of receive antennas. And again, you have a range in which you could resolve the sources. This range depends on it depends on the antenna configuration. For example, if I used a phased array, essentially MT is the number of distinct transmissions. So I should qualify, it's not the number of antennas, but it's the number of distinct waveforms we transmit. In a phased array, we only have MT equals 1, and then you could show that the number of resources, the sources that you resolve with phased arrays, 1 by MT times the sources that you resolve with a MIMO radar in that particular configuration. So to achieve higher resolvability, or you could distinguish more sources, I need to have a particular antenna configuration. And then not only because these are existence results, so they just say that, okay, under some rank conditions, a particular thing happens. But then to essentially see that in practice, you should also need receive processing or even the transmit processing for super resolution parameter estimation. And then, of course, the receive processing depends on what we transmit. And so this leads to the waveform design of the radar. And radar being an active sensing, so you have the capability to design the waveform and also the receiver processing. So in a waveform design, so you can assume that you have n transmissions per decision, n snapshots, if you want to call, or n number of chips in a pulse coded modulated waveform system, or in a FMCW, for example, is the number of samples at Nyquist rate. So what we do is essentially we transmit code S, which is the number of antennas times the number of snapshots or number of transmissions. So we assume that some things with regards to the target are fixed here, that the target does not move range cells, or the Doppler is not appreciably different in within this time. And then to achieve the higher resolvability, the matrix S should the necessary and sufficient conditions only require this matrix S to be linearly independent. But if I want to implement and sort of show the results, we require an additional requirement. We have an additional requirement that is that the S is orthogonal for non-separate transmissions in the sense that all the rows of S are mutually orthogonal. That means the receiver can somehow distinguish between the transmissions of the different antennas. So this could be done in time, frequency, or code. Different kinds of resources need to be used for generating a matrix S in here. To substantiate this, I show here this picture from a paper, which shows the Kramer-Rao bound, which tells the the estimation accuracy for DO estimation, and then it tells us how many the Kramer-Rao bound for 5 transmit, 5 receive with a particular when we sweep over a number of sources. So it can be seen that when when we use these numbers, the phased array can only generate about 2 sources, resolve 2 sources, and then here you could see that after 2 sources, the Kramer-Rao bound just becomes unbounded. That means the estimation accuracy is being lost, and so essentially you cannot estimate. And then on the other hand, if I use a MIMO, the estimation accuracy is pretty much valid for a lot of sources. Again, at 12, it starts to increase, and this is the limit that is provided by this formula here. Okay, so now essentially 2 things are needed to improve the resolution, angular resolution. One is the antenna configuration and the code design. So when we sort of look at this code design here, it's a matrix that we need to design. And the question becomes, is it something that is related to, is it related to pilot contamination? There's something that we could explore a bit. So what should this N be? This is the number of transmissions used to probe the channel. Typically, it is the one that it gives us the compression gains or the SNR improvement, like a maximal ratio combining. It's like essentially a rake receiver you're trying to correlate with all the receptions. So larger N means higher improvement in SNR. The reason we focus on SNR in radar is that the radar front end, the SNR is typically negative. This is because you have a 2-way propagation, and also because of the non-coherent radiations, reflections, we have a 4th law of power decay unless there's a squared law in communication. So essentially, I need to build up the SNR for the processing to detect anything interesting. And then when you have larger number of snapshots, then we look at the consistency problem, in a sense that typically when we do DO estimation with super resolution algorithms, we use statistics, and in the absence of ensemble average, we sort of look at sample averages, and we would require a lot of samples to sort of get a good estimation or a consistency in the estimates. So if I don't have a lot of large N, then we should change the algorithms to look at different algorithms. Which there are some algorithms which use single snapshot and so on and so forth. But then when we have larger N, that means the radar is transmitting for a lot of time. And typically in a radar, when something is being transmitted, the receiver is shut down because there's going to be a significant leakage of energy. So in such situations, until the radar has completed the transmission, the receiver will not start picking up the reception. So what would happen is that if there's a target within this range, then it is lost. So that means that it increases the blind range. There are some targets which are near that you cannot detect if I have a larger pulse width. It also reduces the range resolution because you're transmitting over a longer period of time. That means you're using lower bandwidth, so the range resolution. And of course, you have increased complexity. So that means there are some trade-offs between what should be an ideal N. This comes from the system level and the design. So essentially, we are looking at waveform as a code matrix, and then you could also look at it as a set of pilots where you could impose these orthogonality constraints on the transmissions, row orthogonal transmissions, and for a limited N, where if the system requires you to have very small numbers of N, then it again comes back to the problem of pilot contamination, because you have very few, it's a small space, and then you need to find a lot of orthogonal sequences with some structure. For large N, if I can have a large N, that then any randomly selected waveform suffice. You could choose anything at random, and if the N is large, if the length of the vector is large, more or less we could say that its inner product goes to 0. But would that suffice? Well, probably not in a radar, because the waveform that we have been looking at is now being looked at only from one aspect, which is range, which is just correlation. But then there is the other aspect, which is the Doppler, which results in ambiguity. So there's another dimension that we have not explored yet. So there is there's very little work done in this aspect to see would the waveform design in a massive MIMO radar correspond to anything related to a pilot design in a massive MIMO communication system? If so, under what conditions? If not, what needs to be done? And what else, what additional complexity that the radar sensing brings for the pilot design or the waveform design? So this is pretty much unaddressed, and essentially this talk is to show that a lot of things have not been addressed, rather than showing many results, because there are not many available. And then, okay, so more antennas, very clear. It was obvious that we're going to have better beams. There's also more antennas in radar, which is giving another use case, which is less obvious. This is a paper from Fulvio Gini and et al. Stefano Fortunati, very recent paper. Here, the problem is more from a receive side. So you would have a classical radar transmission and reception, and then we form a hypothesis, the null hypothesis, where it would receive not just noise, but some perturbations, which could include clutter, ground clutter, or any other interference. And then the true hypothesis, where we would have the target returns, and of course corrupted by interference, and we would have k such snapshots. Classical estimation problem is to find the test statistic and then decide on the hypothesis based on the likelihood ratio test, and then evaluate the probability of and then find out the probability, or you can detect the lambda based on the probability of false alarm. The problem here is in evaluating these statistics here. This is now only receive-centric problem. The problem is in evaluating these statistics. So the idea is to find the optimal threshold that enhances the detection probability for a given false alarm. So if I want to do this, I need to solve this integral equation here. And for that, we need to have the conditional probability under the null hypothesis of the test statistic. This is very difficult unless certain assumptions are made on the hypothesis. All the hypothesis measurements are IID, which typically is not, because, for example, if it's clutter, or for example, if it's ground clutter, it's the same object that's reflecting every snapshot, so it's not necessarily IID. Some technical things on the functional form of this PDF needs to be known, either exponential family or the Gaussian, etc. Target return strength needs to be constant, which is clearly not the case, because as the target moves away, the strength goes down, and more snapshots than antennas, which also many times is not true. So these are restrictive assumptions. And then when we have the number of transmit and receive antennas go to infinity, this is a classical, very large aperture. These detection tests are simplified, and these restrictive assumptions can be omitted. So this is another perspective on having large apertures, but mostly from a receive perspective in sensing. Okay, so and then as I said, massive MIMO and radar itself is sort of quite novel. So in JRC, it's even more, I would say. Very few works. This is one work that looked at massive MIMO for JRC. So the idea is as follows. So you have a massive MIMO base station with surveillance capability. So you clearly serve the users on the ground, and you have the surveillance capability to sort of track or detect and track aerial objects, for example, the UAVs. So the problem, they use separate waveforms for radar and communication. So here is the user beamform data with the beamforming vectors, and then you have the radar beamforming vector. So you form separate beams, and with appropriate weighting functions, and then you would sort of probe the UAV channel and communicate to the base station, sorry, the users. So you have a large number of antennas, so this would help us support multiple beams and also offers degrees of freedom to minimize the interference. So this has been an initial work with and the system model and the way we choose the different waveforms, so the different weighting beamformers sort of indicate a trade-off. It is a first work, so it would be interesting to further explore and optimize the different parameters in this problem. Another work is massive MIMO in GRC, where it looked at analog digital hybrid beamforming. The problem is as follows. So the GRC for a vehicle to vehicle or vehicle to device scenario in the terahertz. So, and then you would have antenna array, two-dimensional antenna array mounted onto a vehicle for performing both the transmit to the communication and the radar tasks. So the idea was to use, since it's going to be massive, the idea was to look at hybrid beamformers for this scenario. Here's the scenario. Then different architectures were explored. This was the first one is the fully connected, and then array of subarrays, and then group of subarrays. Three different architectures bringing in the concept of analog is hybrid digital and analog beamforming. And so the new thing was to sort of include the radar sensing, the sensing sensing figures of merit into the design of the analog hybrid digital beamformer. And then the paper looks at both model-based and deep learning-based methodologies. I'm not going into the details. The paper is on archive, I think also available, published. So, but it gives us a sense of what is happening in the literature with this, in this case. So with that, there's much to review, but much more to investigate. So with this, I would sort of make some initial conclusions. So massive MIMO has been well studied for communications. There's been limited studies for radar per se. So you could look at massive MIMO for GRC as a natural extension of massive MIMO for communications, and then you just include radar-oriented constraints. This works well when sensing is an add-on to the communication. Some works we have already looked in the literature. But the question is that just to figure out if the scenario requires large arrays for sensing only application, then it makes it interesting that it's not just an add-on, but it's also imposing additional requirements. And then it brings challenges in the waveform design. For example, if you want to look at automotive applications, you want to communicate, but then you need to have very good angular resolution. So it's just not an add-on, and that makes the problem interesting. Again, you have classical challenges, which what design criterion to use, what information is available for transmission, so on and so forth. And then now if you're going to combine radar and communication, then it if everything is co-located, then you always have the problem of full duplex operation of the system. So when the communication is when you have the communication mode, then the radar receiver is still on, or then you would have, which is because it's both the radar and the communication receiver, so you would saturate with massive MIMO the receiver front ends. So something that needs to be understood in this context. So of course, further exploration on the different topologies, so on and so forth. Essentially, everything is open. First thing we have to understand is if it's absolutely necessary, and then proceed. So as they say, when I have a hammer, everything should not look like a nail. So this is what I would sort of conclude with. So with this, I thank you. So if you need further information on the activities, here is the information, and we also have this new book that's available for pre-order, but it stops at MIMO. It does not go into massive MIMO. So with that, I stop the thing. So open for questions.
Thank you very much, Bhavani, for the very nice talk. I guess we can open the floor for a few questions. Okay, so whilst we wait for the questions, you mentioned at some point the design of the use of pilots for radar and massive MIMO.
Yes.
Yeah, so one thing that naturally comes to mind when you think about joint communication and sensing is whether you can use the actual code words, especially when the radar is kind of co-located with the transmitter. So why not use the code word as kind of a radar waveform? So maybe it would be interesting to look at the properties of, I don't know, good codes, see if they are also good probing signals. So
indeed, there are two different things that we should look at. One from the perspective that if you're going to use the entire waveform, you're sort of doing a simultaneous transmission reception. So are the systems capable to handle that? And the other one is, as you mentioned, whether the code words are good for the radar tasks. So essentially, do they have a good ambiguity function? Not everything has good ambiguity functions. Maybe you can use them to get good performance in range. You could detect the delay well, but probably you cannot detect the Doppler, or depending on the Doppler, you could detect the delay well or not. So essentially, it needs a bit of tuning to get the right code word or the right waveform for the sensing for the sensing task. In that context, there was a work by a colleague where they looked at the Golay pairs, which are used for 802.11 AD in the preamble, and it was good for correlation, but not so good for the radar tasks when we had Doppler. So they had to tune it a bit, and then they came up with a different set of sequence that still served the purpose for the communication. It was a preamble, so it was for frame synchronization. It still served that purpose, but also was used for radar.
Here. Thank you very much.